That's weird. My sound is off on my computer. Like I have my sound off on the computer. Whoa. But if I turn it off there, it's still on. Oh, that's going to be annoying. Hold it, please.
I know people probably already asked you this.
Yowza! Did you hear that? Holy chicken nuggets!
I heard that from over here.
Yeah!
What?
I just got like electrocuted right there.
Are you okay?
Yeah. Although there was one time I was setting up my computer in my dorm room at college, and I was trying to plug something in, and I was like, the plug was back behind, and I was like trying to reach it, and then I was trying to feel for where like the things were, and I completed the circuit, and it was like, like my arm went like totally like this. Oh gosh! And then I like was laying on the floor, and I was like, okay, am I okay? Okay, I'm okay. Okay. All right, and we're back. So today's gonna be kind of an odd day because we're gonna connect what we've been doing with calculus to what we can do using a computer graphing system like Desmos. So I want everybody to go to you can just go to desmos.com. It's bringing me right to calculator, but if I just go here, beautiful free math. So it says it there. You can just go to your graphing calculator. I love using Desmos. I love using Desmos because it's so nice and easy, and it picks out points for you very clearly. So here's what we're going to do today. We're basically going to combine what we can do algebraically with calculus to what we can see on Desmos, on a graphing system, on a graphing calculator. I know this is going to be kind of weird today. Yeah. There's not many notes that you're going to be able to take today. So the method we used to sketch curves in the preceding section was a culmination of like everything that we've studied this year so far, right? If you think about what we did in the last section, it's like we had to use every bit of information that we've studied this entire year, right? We had to talk about limits, we had to talk about derivatives, we had to talk about second derivatives, whatever. We had all sorts of things, and the difficulty of the graphing came with the difficulty of the function that we had, right? Because with the difficulty of the function came difficulty of the derivative. Okay, the graph is the final object that we produced. In this section, our point of view is completely different. Here we start with a graph produced by the graphing calculator. Now they kind of present it as if you are using your handheld graphing calculator. Like in the book, it talks about changing your window to certain things and blah, blah, blah. But in my mind, see, I was going to go that route. But in my mind, I'm like, why not use Desmos? Why not use our computers? If we're going to be looking at a graphing system on a piece of technology, why not use Desmos? Because it's so nice to use. Why actually try to use our calculators? Because it just is so much easier, and you'll see why here in a second. So what we're going to do is we're going to use calculus to make sure that we reveal all the important aspects of the curve. And based on the things that we know from algebraically working with those functions through calculus, we can highlight those pieces to the graph. Okay. With the use of the graphing device, we can tackle curves that would be far too complicated to consider without technology. The theme is interaction between the calculus and the calculators rather than just doing it on our calculator and doing it with calculus. It's how do we combine those things? How do we think about those things in the same respect? So what we're going to take a look here is our first function. F of x is equal to 2x to the 6th plus 3x to the 5th plus 3x to the 3rd minus 2x squared. Now, we could use calculus to find the derivatives here, right? We could use our algebraic work to find the derivatives, and we will do that here in a second because this one is not too bad. This is just polynomial, right? So finding the derivatives of the polynomial, either first or second derivatives, it's not going to be too bad, and we will do that so that we can create the derivative so that we can graph it. But let's first start going by graphing this function, okay? I'm going to go like this. I'm going to split screen it. Ooh, that got really small. I'm going to hide this. Okay, 2x to the 6th. And now the nice thing about Desmos is you don't even have to like say y equals, you can just start 2x to the 6th plus 3x to the 5th plus 3x to the 3rd. Oh, caret up is shift 6. Shift 6. 2x to the 6th plus 3x to the 5th plus 3x to the 3rd minus 2x squared. Okay. It says use the graph of f prime and f double prime to estimate all maximum and minimum points and intervals of concavity. So here's what you're going to be doing in your homework. Notice there's only 4 problems for your homework, right? What you're going to be doing is you're going to have it. Sorry, did anybody? Well, I guess the function's right there if you need it. What you're going to be doing in the homework is you're going to be doing some algebraic work and then doing some work on Desmos and screenshotting what you see on Desmos and putting it into like a Google Doc or a Word doc. I don't care, whatever you want to do. Okay. And then that's what you're going to submit for your assignment. So here's what I want to think about. The important pieces of the function here are the maximum and minimum values. And you want to know what's really nice about Desmos? Look, you can just like click on it and it tells you the minimum point, right? You don't have to do like, if I had my like graphing calculator, I would need to like figure out what window I would need, click on the like left bound, right bound guess. But like, look, that is literally how easy it is with Desmos. So the minimum value is negative 1.616 at negative 1.616, negative 15.326. Okay. Oops, can we stay there, please? Stay there. I'm going to click on that. Okay, maybe not. Maybe it's not going to stay. I'm going to click on that point, and it looks like here, something's funky happening in the center there, right? I don't know what's going on. So let's zoom into the center. And it looks like it has another maximum value at 0, 0. And then it looks like it has another minimum value. Now, what are we not showing here? We're not showing inflection points either, right? We're not showing inflection points either. What I see here is a local minimum value, a local maximum value, and then another local minimum value. I don't see any inflection points. But what I can see are, see, look at what I'm trying to identify. I'm trying to identify, use the graphs to estimate all maximum and minimum points in the intervals of concavity. Okay, so what did we just do? We found our graphing, we put our function on the graphing calculator. And if I just simply click on those maximum and minimum points, you can solve for them. So here we go. The minimum point is negative 1.616, or minimum point here, 0.352, at 0.352, negative 0.097. Maximum value at 0, 0. Okay. As soon as I zoom, those points go away. So like maybe if I try to just click on all of them at once. See, this is what I will need to see. I can actually just do this like little fancy screenshot tool. Yeah, go for it. Yeah. I don't want to call people annoying, but you know. Okay. See, here's what I would need to see. If you were doing this on your homework here, I would need to see the original function, and I'm going to screenshot or screen clip, whatever you want to do. And I don't need to see the whole tab, but I do need to see like what you're plugging in and the values there. See, I can do this. But if you wanted to, well, you just search for the snipping tool, right? There we go. You just do that, and this will make it an image for you. Okay. You just hit new. Get out of here. You just hit new, and then you can snip it. But give me all the critical points, and I want to see the function over on the left side. See, so here's my snipping tool, and then you could just, ooh, I don't want to draw. Never mind. Control Z. Nope, that didn't work. How do I erase that? Eraser. I tried to Control Z, it didn't work. But you can right click and copy that, and then paste it into somewhere else, like paste it into a document. Does that make sense? So I see the local minimums and local maximum values. Now, here's where the algebraic piece comes in. I want to find the derivative and then graph the derivative. Because what am I going to see? Once I graph the derivative, where are the local maximums and minimums going to come up? At the zeros of the derivative. So let's now go ahead, and I'm not going to go plug in, so I'm going to do this on the whiteboard. Let's find the derivative of 2x to the 6th. So f of x is equal to, ooh, green. Pick up a green marker. 2x to the 6th plus 3x to the 5th plus 3x to the 3rd minus 2x squared. Let's find f prime. Pretty easy to do here. F prime of x is 12x to the 5th plus 15x to the 4th plus 9x squared minus 4x. Right? Pretty simple. Just a polynomial. Bring it down 12, knock it down 5, bring it down 15, knock it down to 4, bring it down 9, knock it down to 2, bring it down -4, knock it down to 1. And while we're at it, because we're going to need to in a second, so I don't have to get up off my chair again, let's find f double prime. Because it also asks me for the intervals of concavity too. Right? So we can say that this is going to be a 60x to the 4th plus 60x to the 3rd plus 18x minus 4. Now, let's graph those. Let's graph them one at a time and see what happens. Now, I'm going to leave that function there. So to get a new function to graph, I'm just going to enter down. And now let's graph f prime. 12x to the 5th plus 15x to the 4th plus 9x squared minus 4x. While we're at it, so I don't have to keep turning around, I'm just going to plug in f double prime as well. 60x to the 4th plus 60x to the 3rd plus 18x minus 4. Now, it may get, like, look how weird this looks. All these different colors going on, right? So it may be a good idea to hide things as you go. Like, for example, I'm just gonna hide. You could just click these buttons to hide and unhide. So when you're doing your like screenshotting to find of the derivative and the double prime, it might be a good idea to hide your original, or hide, you can hide everything but your double prime, whatever. Okay, so let's think about this is our derivative here. Okay, this is our derivative. So where were the intersection, or where were the local maximum and minimum points? Well, it looks like I had it at 0.3520 and -1.6. What do we see here on the graph? 0.352, 0, -1.616. I want to see this. Okay. I also would like to get I want to reveal all these points, my local maximums and local minimums of my derivative. And you'll see why here in a second. So I'm going to screenshot that in. I would like you to separate them, because that would be a lot in one. And you also can't choose two graphs and reveal points on both of them at the same time. Right. Yeah. Yes, and you'll see why here in a second. I'm going to screenshot this. Okay. And this is my derivative. It doesn't need to be. Okay. You can if you want to, if you want to separate it out, but I can see it. So what do I see here? I see here that the maximum and minimum x values are equivalent to the zeros of the derivative, right? But I also revealed the points that were the maximum and minimum values of the derivative. What are those? Can anybody guess for me? What are the maximum and minimum values of the derivative? The possibilities of inflection points. Yeah, the inflection points. Which would be what if I look at the actual graph of the second derivative? The zeros of the second derivative. Let's take a look and see if that's actually true. I come back here. I'm going to hide my first derivative and reveal my second derivative. I'm going to zoom in. And I'll screen capture this so we can see it all on one page. Come on. Wake up. Come on. There it goes. So we can see this all on one page. Maybe I'll make it a little bit smaller. I know I'm already making it small. But look at what I have here. What do you see as the zeros of the second derivative? Negative 1.22 or negative 1.233. And then look at my maximum value of my first derivative. Negative 1.233. Look at the the x value of the minimum point that I have in my first derivative. Look at the zero of my second derivative. Okay. Also, now we can go back in and look at our first derivative, or sorry, our original function. Let me move this to side. And now my inflection points are at negative 1.233 and 0.19. Let's go back here. Actually, I don't even need to look at the screenshot. I can go back in and just see this. I see that, what was it? It was at negative 1.233. Let's look here, negative 1.233. Look, it looks to be about right. Negative 1. These are going by halves. Negative 1 point. See, and you can click and hold and see exactly where it is. Negative 1.233, right there. Right. Unfortunately, I can't make that point stick. Right. Negative 1.233, somewhere around there. But that is the inflection point. That is the inflection point. That's where it's crossing from concave downward to concave upward. So now I can identify intervals of increase and decrease, points of concavity, and intervals of concavity as well. Or, excuse me, inflection points and intervals of concavity. Okay? Like we had before. Yeah, like write it out. Like you say, okay, because I know that the zeros of the second derivative are negative 1.233 and 0.193. I know that the inflection points are at negative 1.233 and 0.193. I know since the zeros of the first derivative are negative 1.616 and what is it? 0.193 and I guess let me go back to this so I don't have to look at something really small. Here are the zeros, right? You can say that, okay, so I know that it's the intervals of increase or decrease, or sorry, the intervals of concavity are from negative infinity to negative 1.616. I know that it's going to be concave downward because it's below the x-axis. I know that from negative 1.616 to 0, it's above the x-axis, so I know it's concave upward. I know that between 0 and 0.32352, and you can just use all of that. Does that make sense? Use what you see on the screen to define your intervals of concavity, your intervals of increase or decrease. Yeah.
You said the min and max of the first derivative are the inflection.
Yeah.
So you said it was possibly. Why would?
I'm sorry. Those are.
Always.
They are. Yeah. Unless they are somehow undefined within our original function. Yeah, and I don't think because we're doing this in a graphing, it's not the algebraic things are not going to come up. So I think it'll be fine. Yeah, Claire.
So the zeros of the second derivative are also the inflection.
Right. And that's what I want you to see based on all of these graphs, that those x values always match up. And here, take a look when I put the my original function and the second derivative. You know, this is going to kind of be a little weird, but the intersection, like those x values there, that where they line up to be the same, that's actually where the inflection point occurs. I know it looks weird because these are actually pretty steep polynomials, but look here, -1 point, look, the x-intercept there, right? -1.233, where it comes down here, where well, it's not the exactly, but it's really close. That's where the inflection point actually occurs. It's right down there, right? At that same x value, it's where the inflection point is occurring. If I reveal my first derivative on my original function, I see that, look, my maximum value is where the first derivative crosses the x-axis. My minimum value is where the first derivative crosses that x-axis. Look down here, I see, because it's crossing the x-axis at -1.616. If I scroll down, -1.616, that's exactly where that minimum value occurs. Okay, so what are we doing here? We're looking at how does the graph, what did we find algebraically match to what did we see on the graph, and how do those graphs relate to each other? You know, you've got to know that the graph of the first derivative will show you not only the intervals of increase or decrease, it'll show you where the zeros are, which means it shows you where those maximum and minimum points could be. It will also show you, based on the maximum and minimums of the first derivative, where the intervals of concavity are, because I see the maximum and minimum points of that. Okay, so here's what I need to see. I know we're not really like writing a lot of stuff down. Here's what I need to see for each problem. I want to see screenshots of your first derivative, your second derivative, as well as the original function. I want you to reveal all the critical points of all of those, and I want you to show where they line up. It will also ask you to identify the intervals. What's that? Like how the x values all match up. You know what I mean? How the x value matches -1.616, -1.616. You know, I want you to show that those actually are equivalent to one another. And you can use that to write out your intervals. Write out your intervals of increase and decrease, write out your intervals of concavity. Yeah?
So you want separate screenshots other than these of them overlapping?
No, you don't have to show that. I just want you to show, like, maybe draw arrows to it, or whatever you say, like the x values are matching at -1.616. You know, I want you to write that out, like, as an answer. Okay, yeah.
So you want the original, the first derivative, the second derivative, and what else?
I need you to write out your intervals of increase and decrease, intervals of concavity. And I want you to reveal the points on those graphs. When you screenshot it, make sure all of those points are on there. I don't want, here's what I'm saying. I don't want you to graph this, like, here's my first derivative. Let me take off my original. Here's my first derivative. I don't want a screenshot of just that. That doesn't show me anything. I want the actual coordinates. Show me on there. Show me the coordinate here. Reveal the coordinates here, 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 and here. Because those are going to be all of the important pieces of information I would need for the rest of the graph. Okay, that tells me everything, not only intervals of increase and decrease, it also tells me where the concavity is. It also tells me where the inflection points are. Yeah.
Like in our explanation, say we said, like, since the variable points of the second derivative are so and so, that means that there's an inflection point to the original graph.
Exactly.
That counts as like the third part that you want.
Exactly. Okay. Exactly. I want you to explain what those points actually mean within the graph. Does that make sense? Okay. So let's do another one, shall we? Let's take a look at another graph. I know there's kind of a funkier one on here, so let me see. Yeah, let's do this trig one. Okay. Okay. Sine of x plus sine 2x. Oh, and I also, within the work, I want to see if you can find it easily, the derivatives too. If you can find it easily, the derivatives. Sine of x plus sine of 2x. Okay, I'm gonna just get these out of the way. sine of x plus sine of, ooh, what was that? That looked funky. Look at that. That's just sine of 2x. Sine of x plus sine of 2x. And it suggests, I like Desmos because it suggests, like, are you sure you want to put a parenthesis there? Do you want to put a parenthesis there? Do you really want to put a parenthesis there?
Whoa, this is fun.
I know. See, isn't this cool? Now, it's saying I only need to graph it on 0 to 2 pi. You know, that'd be if it was like writing it out. But we're just going to investigate it on the interval from 0 to 2 pi. Okay. So here's my graph. Look, it's actually bringing up points that it's suggesting me to click on. 0.623. Look at what this even does. Man, Desmos, you are so smart. It gives you the x value in terms of radians because it knows I plugged in a sign, so it knows I probably want radians. Now do the best you can. When you click on these, some of them might overlap. So do the best you can. Yeah. There we go. That's a little bit better view of it. Okay. And I want it from 0 to 2 pi. Oh. There we go. Okay. So I'm going to screenshot. This is my original graph. So it's already there. No. Oh, I lost all those points? Are you serious? Like as soon as you click off of it, it goes away. All right. Now,
Oh, man.
did it go away?
Yeah.
I know. So I see 1, 2, 3, 4, 5 extreme values and then 5 more extreme values. Now, I haven't even thought about how this is going to work for my derivative yet. But think about solving this algebraically. So you mean to tell me just from the interval from 0 to 2 pi, I've got 10 extreme values? Yikes. Yikes. No, thank you. Right? That seems like it's going to be very hard to do algebraically. You know, also, let's take a moment. Ow, man, I just snapped myself again. Let's take a moment and try to find the derivative algebraically. Let's do it. What is the sine of x plus sine of 2x?
Yeah.
Okay. Well, this has got a chain rule in it, right?
Yep.
So first thing I'm going to do, I'm going to peel away the layers. What's the derivative of sine? Cosine of x plus sine of 2x. Right? And then I have to multiply by the derivative of the inside. Right? 1 plus, cosine 2x, chain rule again, times 2. Right? So in other words, f prime of x is going to be cosine of x plus sine of 2x times 1 plus 2 cosine of 2x. That's your derivative. You want to see something cool that Desmos also does? Look at this. Look at this. Look at this. D divided by dx of the slash. Control C, Control V. There's my derivative. There's at least a graph of the derivative. I know, coming in clutch, right?
You are hip with the time.
So do we see how, I guess I could have also done this. Take a look here. Desmos is also nice because it's going to like check whether their derivative, you could like check algebraically whether your derivative is right. Like if I would bring another function down, let's see if we actually got this right. Cosine of x, well, that's a 2, x plus sine of 2x. Oh, okay, and parentheses, times 1 plus 2 cosine 2x. Look at that. Yeah, same graph. Right? So I know I got my derivative right. Now, here's the deal. I'm not even going to try to find the second derivative algebraically. Yeah, I mean, I'd have to use a product rule in there, and no thank you. Okay? But you know what you can do? D over dx of Control C, Control V. And there is F double prime. Now, beautiful math. Let's pause for a moment and go back to our just the first derivative. Okay, just the first derivative. What are the key pieces within the first derivative? Well, it's all and I'm just looking at from 0 to 2 pi. So 2 pi, 6.28 somewhere in there, right? So this is 7 here, so 6 point somewhere right here. So this is probably one interval. So I'm going to click here, click here, click here, 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 here. Oh, of course. But let me zoom in a little bit. If you want to take a couple screenshots of this, you can, because obviously, look, like there's a bunch of points that I'm thinking of. It might be a good idea to do this, like just do your zeros as a screenshot, because what are the zeros of your first derivative again? Your maximum and minimum, your intervals of increase and decrease. That's still a lot, isn't it? Right? How does that match up with your original function? Didn't we say, wow, there was 10 extreme values? How many x-intercepts did we have between 0 and 2 pi? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Hey, look at that. Those match up exactly. And if I were to go in and see again, I'm going to screenshot this before I lose it. These come in so big when I do that. Take a look at the x values. Look at how they're matching up. 0.623, 0.623, pi over 2, pi over 2. Oh, I missed that one. Pi over 3, pi over 3, pi over 2, pi over 2. They're all the same, 2 pi over 3. Even this 2.519. Okay, those are all matching up. I want you to show that the zeros of the derivative are equal to the extreme values of the function. Okay, and then we can go back here and say, okay, well, that also means that the maximum and minimum values of my derivative are my inflection points. This one has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 inflection points. 11 inflection points. Holy cow. Right? Do those match up? Let me screenshot this. Do these match up with the actual zeros of my second derivative? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yes, they do. right?
You had 11 on the line.
Did I say 11? Oh, maybe. Oh, that's right. It's right there. It's at 2 pi. 11. There you go. And then we screenshot that and you show, okay, those x values are the same as what I showed here. Yeah, let me just show that there. 0, 1.3, 0.79, 1.3, 0.79, 1.3, and so on. Okay. And I can relate that back to my original graph. I overlaid that graph with the graph of the original. Look at the zeros. Every time where it crosses the x-axis, the second derivative crosses the x-axis, there's an inflection point in there. Look, do we see where it's going from concave up to concave down? Concave up, concave down. Here, this intersection here, this intercept here. There's an inflection point there, an inflection point there, an inflection point here. It's happening at 0, right? Happening here, all of those places. So we can see the inflection points based on the different graphs that we choose. Okay, does that make sense? So is it clear what I want from the for the homework? I want a lot of different screenshots. Yeah, give me like a page worth of screenshots for each problem. Does that make sense? Like you can organize it in a table, however you want to organize it, but I want to see screenshots of original function, first derivative, second derivative, all the points revealed, and then give me an explanation about how they relate. Okay, and give me an explanation on how they relate. Okay, does that make sense? Cool. All right, that'll be it. So tomorrow, I'm gonna let you work on this tomorrow. You don't have to do that tonight if you don't want to. I'll let you do that tomorrow in class. We're gonna review on Tuesday, and then we'll quiz next Wednesday over just these 2 sections. Honestly, the quiz you can expect. Can I give you 2 graphing problems on a quiz, or is that too mean of me? Depends how bad the second derivatives are. Okay. Well, I'll think about then. But then I am also going to give you a portion where you'll complete it that night. I'm going to give you a graph to show me, or I'm going to give you a function to show all the critical points and whatnot. Do basically what we're doing here. Okay. And then you'll turn that in. That'll be part of your quiz grade. Cool. And great. Hold on. I gotta turn off the video. What did you say?
Hi.